Hello students, Mr. Courtney here again. In this video we're going to be looking at electron configuration again, but this time we're going to be paying attention to orbital diagrams. That is how electrons are actually arranged in their orbitals. So that's what we're going to be looking at in this video. Now there are a couple things that we need to do first. One of the things we need to pay attention to is the Aufbau Principle, and we talked about this when we did the first set, when we did the electron configuration already. We talked about electrons being filled in the order from the lowest to the highest energy levels. So electrons are added to the lowest energy possible because we said Aufbau is a German word for building up. So we start with the 1s. In the second energy level, we add to the 2s, then to the 2p. Third energy level, 3s, 3p. And here comes where there's some overlap of the energy levels. The 4s, then the 3d. 4p, 4d, 4f, and so on. So we go on in that vein. Okay, so that's just talking about in terms of how we add the electrons in based on energy. So we add to the lowest energy level possible. And we'll see this here. We'll see there, if we continue going on, we'll see some overlap here again. Okay, so we'll see some overlap here. So this one doesn't actually fit in after the 4D, but we'll see that later on when we talk more about it. The second thing we need to pay attention to here is Hundra rule. One way of stating it is that we must half fill each orbital before we can fill any one. So in our p sublevel here, we have 3 orbitals. So we're going to add 1 electron to each orbital before we can start pairing. So if we have 3 electrons in the p sublevel, or in the p orbital here, so in the p sublevel we have 3 electrons and we have 3 orbitals. So we must place 1 in each orbital before we can add another. So if I were to add another electron here, and we use the arrows to represent electrons, I'm going to add it here because I've half filled all these already. Okay, so we've half filled all these. So once we've half filled, we can go back and add the electrons to the other energy levels. To pay attention to Pauli's exclusion principle. No 2 electrons in the same orbital can have the same spin. What do we mean by spin? Let's just simply say orientation. Notice the direction in which the arrows are pointing. One arrow is pointing down, one is pointing up. So they don't have the same orientation. They don't have the same spin. One is pointing down, one is pointing up. And this one is by itself, so it's just pointing down. But if you have 2 electrons in the same orbital, these 2 electrons are in the same orbital, they cannot have the same orientation or the same spin. What is an orbital diagram, or sometimes called a box diagram? It shows us the actual placement of electrons in the individual orbitals. So how are the electrons arranged in the 1s, in the 2s, and in the 2p orbitals? We use the boxes to represent the atomic orbitals, and we use the arrows to represent electrons. So for example, carbon has 6 electrons. When we add the electrons to the orbitals, we start at the lowest energy level, which is our 1s. We put 1, 2. That's filled. We still have 4 more electrons to add. We go on to the 2s. We add 1, 2. Then that's filled. We go on to the 2p. 2p, or the p sublevel, has 1, 2, 3 orbitals. And we only have 2 electrons. So I add 1 electron. Now I cannot add the second electron here. Remember, we need to half fill before we can do that. Okay, so we need to half fill. Hundra rule. We need to half fill. So I add 1, then I go on to the next orbital and I add the other electron there. And that takes care of my 6 electrons for carbon. 1, 2, 3, 4, 5, and 6. So this is just another way of showing orbital diagrams, and we're using the element sodium here as an example. Sodium has 11 electrons. We filled our 1s orbital, so 1s2, 2s2, 2p6, 3s1. So that's the electron configuration for it, for sodium. So this diagram here shows us like this. So it goes up. It shows us in terms of the energy. So it tells us the 1s has the lowest energy, then the 2s, 3p, 3s, I said 3p here, sorry, 2p, 3s, 3p, and 4s. Now, if we want to write it another way, that's one way of doing it. Another way of doing it is this. We write our 1s has 1. We write everything on the same level. So we're just going to write them across like this on the same level. So that's 1s, 2s, 2p. Our p has 3, 1, 2, 3. Then we go to our 3s, which would have 1 orbital. Now we know this is 1s2, 2s2, 2p6, 3s1. Now in some cases you'll see, like we said, the box. People will put box. And this box is kind of small. Can make this one a little bit bigger. No. Do we necessarily have to put the box? No. You don't necessarily have to put the box. And I'll edit the 3s also. Okay, so there we go. So in terms of adding our electrons now, we're going to add our 1s1. Notice they have opposite spin, opposite orientation. 2s2. Now we get to the p. So when we get to the p's, now we need to half fill. 1, 2, 3. So I've half filled each orbital in the p sublevel. Now I can go back and fill them. 2, 3. And that gives us 3 in total. So that's our 6. And then our 1. And that's how you can write it. And again, you can also do it without using 1, 2, 3, 1 without using the boxes. So if this was at the top, we just go 1, 2, 1, 2, 1, 1, 1. And I'm still going to do it the correct way, even though I know what it's supposed to be. Even though you know it's filled, get into the habit of half filling first before you fill. So that way you remember exactly what you're supposed to be doing. And 1. So that's another way of writing it. So it's the same 1s2, 2s2, 2p6, 3s1. Alright, so let's look at the orbital, drawing the orbital diagrams for the following atoms. We start with nitrogen. So we find nitrogen on the periodic table, which is here. First we write the electron configuration, and then we can draw our orbital diagram. So we start with nitrogen. Its first energy level is filled, so that's 1s2. And we enter the second energy level, 2s, and 2s is the sub-level s is filled, so that's 2s2. We go into the p block, and it's one element 1, 2, 3, so that's 2p3. So now we can draw in our orbitals, 1, 2, and 3 in the p. That's our 3 here. And remember I said I'm not necessarily going to draw the boxes. So we add our electrons, 1, 2, 1, 2. And we have 3 electrons, so we need to 1, 1, 1. And that's our orbital diagram for nitrogen. If we do the same thing for oxygen now, oxygen is just one more electron than nitrogen. So it's going to be our 1s2, 2s2, 2p4. We put in our orbitals 1, 2, and the same 1, 2, 3. We add our electrons 1, 2, 1, 2, and we have 4 to add in the p. Remember, half fill, 1, 2, 3, and then we go back and fill 4. So that's our orbital diagram for oxygen. Alright, so let's do manganese. Now we find manganese on the periodic table here. No, it's a bit much to write. So we can go the 1s2, 2s2, and I'm not sure in the first energy level on my periodic table yet based on where I moved it, but we can see 1s2, 2s2, 2p6, 3s2, and we can continue going on and on like that and until we get it. But in the essence of time, and so we can also use our noble gas configuration. So what is a noble gas before manganese? Argon. So we write argon in square brackets. Then we write the configuration. So that's argon. Then we go to 4s2. 4s2. And then we go into what? 3d. And that's 3d5. So that's 3d 1, 2, 3, 4, 5. So that's 3d5, 3d5. Put in our orbitals. We have 1 here, and we have 1, 2, 3, 4, 5. We start adding our electrons. That'll be 1, 2. And we have 5 to add, so we're going to add 1, 2, 3, 4, 5 orbitals. And there we have it for manganese. Okay, so let's go on to next element, GD. So we're looking for the element GD, and GD, if I can remember, it is gadolinium. Yeah, okay, I think so. I think it's gadolinium. I hope so. I hope I'm correct on this one. So again, it's a lot to write, so all we can do is write the noble gas configuration for it. And the noble gas before gadolinium is what? Xenon, because remember it's going to fit into here, right there. So we start with xenon. Let me go down a bit more. Okay, for some reason I cannot erase this, so let's just do this, and I'll do it at the bottom on the white spot. So we do xenon in square brackets. Then we go to the next energy level, which is 6, so that's 6s2. Then we have to fill, we go into the F, and it's 4f, and that'll be 4f8. There you have it, 4f8. So we write it in 4f8. Let's draw in our sublevels. 1 here, and how many are we going to have? 7 in the F. 1, 2, 3, 4, 5, 6, 7. Now we need to fill. 1, 2, and we have 8, so we need to half fill. Even though I know 1 is going to end up back here because we have 7 and 1 is 8, I'm not going to fill it in. I'm going to go through the process. And that's what you need to do. So get used to half filling them first. So that's our 7th, and then we come back and add our 8th, and there you have it. Now we're going to look at the electron configuration of ions. First, we need to know what ions are. Before we define ions as atoms with a net charge, we're also going to add today that it could be groups of atoms, and we'll see why that comes in handy later on. Ions are formed when atoms either gain or lose electrons. Why do they gain or lose electrons? They want to become more chemically stable. So they want to become more chemically stable, and the way they can do that is by either gaining or losing electrons. Atoms are most stable when they have a full outer shell, and that's what we call, they're going to have 8 electrons, so we call that the octet rule, like octopus, octa. Alright, meaning 8. So they have 8 valence electrons. 2 plus 6 is 8. Again, if you look at your periodic table, we said that all the noble gases have 8 valence electrons. So they want to obtain a configuration that is similar to the noble gases, or the same configuration of the noble gases, not similar. So they want to have a noble gas configuration. And that is when they can be chemically stable. Alright, so let's look at writing electron configuration for ions. We have two ions here, fluoride and strontium ion. So we're going to start with the fluoride ion. Here's what we're going to do. We're going to write the fluoride ion and the strontium ion as normal, and we show how they lost their electrons. Now we have to remember, if they have a negative charge, that means they have more electrons than protons. So fluorine, or the fluoride ion, has more electrons than protons. The charge, since it is minus, or let's say -1, it tells us that there is one more electron than proton. Strontium +2 tells us there are two more protons than electrons, or two less electrons, since we're dealing with electrons here. We have two less electrons than protons. So let's write fluorine normally. Let's see what fluorine will be normally. Fluorine is here, so that's 1s2, 2s2, 2p1, 2, 3, 4, 5. So let's write that in. 1s2, 2s2, and 2p5. So that's what it should be normally. But since it has a negative charge, it tells us there's one more electron than normal. So what that means is that it is not 5. We're going to have actually 10 electrons. So that's 2p6. So that's what it should be. 1s2, 2s2, 2p6. And that is for the fluoride ion. If we look at strontium. Okay, so strontium is here. And we're going to write the whole thing for strontium. So we start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that takes us up to here. Then we go on to our D. So that's 3d10 now. 3d10, 4p6. So that takes us to the end here. Sorry, here. 4p6. And then we come to 5s2. Now, since it has two less electrons than protons, that means we've lost these two electrons. So this here is a configuration of it. And if you look at it, 5s, 4s2, 2p6, 3d10, 2p6. It's the same configuration as krypton. So this has the same configuration as krypton. So this is like krypton. Go back to fluoride ion. 1s2, 2s2, 2p6. This is the same configuration as neon. So when we think of isoelectronic, what does that mean? So when we talk about isoelectric, we talk about having the, and that's not what I want to do. Okay, let's fix this. Talk about having the same electron configuration. So they have the same electron configuration as those noble gases, or the ions having the same electron configuration as another element. Alright, transition metal ions. When transition metal form ions, the valence electrons are not lost from the highest energy level. So let's look at this example. Let's look at iron 2. So iron 2 would have the electron configuration of, we're going to write what iron should look like. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 6. So that's what iron would look like normally. But it has a charge of +2. That tells us we have 2 less electrons. So where are we going to lose those 2 electrons from? Those 2 electrons are lost from the s orbital. So that's minus here. So it would have the same electron configuration as the noble gas before it, which is argon. And you can double check on your periodic table. So we can rewrite it as Ar, argon, 3d6. So we see here the electrons were not lost from the d orbital, which is the highest energy level here. It is lost from the 4s orbital instead. So now we're going to talk about paramagnetic versus diamagnetic. So para versus diamagnetic. And that depends on whether there are unpaired electrons in an atom or not. If they're diamagnetic, they have all the electron paired. So all the electrons will look like this. So all the electrons are going to be in pairs. The electrons are coupled up. Whereas if it's paramagnetic, you have unpaired electrons. So they're going to look like this. Somewhere in the electron configuration, we're going to have unpaired electrons. So they are unpaired. So they are like singles. So diamagnetic contains only couples or paired electrons, and paramagnetic could contain couples, but they're going to be some singles. Once there are some unpaired electrons, it's going to be paramagnetic. Okay, so let's look at determine if these elements are diamagnetic or paramagnetic. So we need to write their electron configuration and show their orbital diagrams. So we start with magnesium. The element before magnesium, the noble gas before magnesium is neon. So neon in parentheses, in square brackets, and then it's 3s2. So we add our electrons. No unpaired electrons, so that means it is dia. So it's diamagnetic. Let's do iron. We did iron just a while ago. We did the ion of it, but the noble gas before iron is argon. Then we go to 4s2, 3d6, 2, 3, 4, or 5 orbitals in the d. Add our electrons, change of color, so 1 and 2, half fill, 2, 3, 4, 5. Remember, even though we know we'll pair up, we need to half fill first to get into the habit. So we do that, and we do have unpaired electrons. So that makes it paramagnetic. Let's do cadmium. Cadmium, the noble gas before cadmium is krypton, so Kr in square brackets, and that's 5s2, 4d10, and here we see all paired because we have 5 orbitals. 5 divided by 2, or 10 divided by 2. 10 divided by 5 is 2. It's 10 divided by 5 is 2. 5 divided by 10 divided by 5 is 2. 10 divided by 2 is 5. So we see that it's filled. There are no unpaired electrons. Kind of got myself tied up there a while. No unpaired electrons, so that means it is dia. In this case, we didn't necessarily have to draw it. For phosphorus now, we noble gas before phosphorus is neon. 3s2, 3p3. No unpaired electrons, no unpaired electrons. We have 3. They're going to be unpaired electrons, so that makes it para. So again, unpaired electrons. Once we have unpaired electrons, it's going to be paramagnetic. And we have all paired electrons, it's going to be diamagnetic. Now in chemistry, we work with a whole set of solutions and chemicals, and we make solutions, we make substances, and we end up with colored or clear solutions. What determines if an ion or an element will produce a colored solution or a clear solution? It has to do with whether it contains unpaired d electrons or not. So only elements or ions with unpaired d electrons can produce colored solutions. So that means where are we going to find these elements? Which elements on the periodic table have a probability of producing colored solutions? So if we think of the periodic table just as a basic outline like this, remember this is the S, this is the P, and this is the D, and we have the F down here, the F's down here, right? So if we remember this, so only elements within this region here have a probability, and this is what we call the as best as I can write. The S looks like an 8, but this is actually an S here. Okay, so that only the transition metals have the capability of producing colored solutions. How we determine that? So potassium, and that should be the potassium ion. Okay, so K plus. If you write the electron configuration for that element, the noble gas before potassium is argon, AR square brackets, and we go to 4s1. That is what potassium should look like, but it has one less electron, so we lose the s electron, so it's just electron configuration of argon. No d electrons at all, whether paired or unpaired, so there's no d. So we know right off the bat it's going to be no color, it's going to be clear. Okay, gallium plus 3. Argon is the element before. Argon is very, very popular today. 4s2, 3d10, 4p1. But since it has a charge of plus 3, it means it lost 3 electrons. 1 and 2 would be 3. We have d electrons, but all of them are going to be paired, so it would be clear. Cobalt. Again, the element before cobalt is, the noble gas before cobalt is argon. 4s2, 3d7. And it's cobalt plus 2 means we lost 2 electrons, and we're going to lose electrons in the 4s orbital. So that leaves us with, yes, we have d electrons. Odd number. D is unpaired, so that's going to produce a color. Now some of you may be asking, do we know what color? Can we predict the color? No, we cannot predict the color, but we can predict that it will produce a color. That ion will produce a color when dissolved, when it's in a solution. All right, for zinc, the noble gas before zinc is, you guessed, argon, without looking, because that's a trend we're following. 4s2, 3d10, plus 2 charge, loses 2 electrons. Where do the 2 electrons come from? The 4s orbital, we lose that. Even number, so that means all our electrons will be paired, all our d electrons will be paired, so this is clear. Now there are some exceptions when we're writing electron configuration, and this applies only to transition metals, and it has to do with the fact that there's a certain stability associated with half-filled and filled orbitals, and in this case half-filled or filled d orbitals. Alright. So elements in the same column as copper and chromium are the ones that exhibit that property, that exception. So let's look at some examples. Okay, so let's look at some examples. We're going to start with copper, and we're going to write what is expected and then the actual. So copper, use a shorthand formula or the noble gas formula. Okay, argon in parentheses, 4s2 and 3d9. 4s2 and 3d9, we have 5 orbitals. 5, okay. So that's 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what this is what we expect for copper. Now copper has 9d electrons. So what's gonna happen here? Strange thing happens. We take that d, that not the d, sorry, but that one electron from the s orbital actually is moved into the d orbital to fill the d orbital and make the element more stable. So what we actually see is argon 4s1 3d10. Okay, so let's look at what we actually see. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's what we actually see. So as we said, there is some stability with a filled d orbital as to an unfilled. So there's more stability here in this arrangement than in this arrangement. Okay, so for chromium, the noble gas before chromium is argon. Okay, if I get it right. So we have argon in square brackets, 4s2, 3d4. So we have our one orbital, then we have our 5 orbitals here. So we add our electrons, 1, 2, 1, 2, 3, and 4. So what happens here is that one electron from the s orbital is moved up to the d orbital. So what we actually see is this. It's argon 4s1 3d5. So we have a 1, 2, that's all 5. So this arrangement is more stable than this arrangement. Okay, so what we see is argon 4s1 3d5 instead of argon 4s2 3d4. So in the final example here, we have silver. What I'm going to write is just the electron configuration as expected and actual. So silver is below copper. The element, the noble gas before silver is krypton. I had to double check for a minute. Krypton. And then we go to, so from krypton we go to 5s. 5s2, 4d, and we expect to have 4d9. So that's what we expect. So what do we actually get? And what I guess you guessed it correctly. So we'll have our 5s and our 4d, but it would be 5s1 and 4d10. Okay, so there you have it. So in this lesson, we covered orbital diagrams. We talked about Pauli's exclusion principle, Aufbau Principle, Hund's rule. Aufbau Principle is what tells us the order in which electrons are added. We add electrons to the lowest energy orbitals first, and then we move on to the higher energy orbitals. Hund's rule. We add electrons to the orbitals one at a time. We have to half fill our orbitals before we can actually fill any one of the orbitals. So each orbital must contain one electron before any one of the orbitals in that sublevel can have 2 electrons. And Pauli's exclusion principle tells us that no 2 electrons in the same orbital can have the same spin or the same orientation. We looked at drawing orbital diagrams, the configuration of ions. We talked about octet rule. We even looked at isoelectronic, and we looked at the exceptions to the rules in terms of electron configuration, which is the last thing we did here. We talked about which ions are capable of producing colored solutions, and these are those which have unpaired electrons. Diamagnetic versus paramagnetic. If an element has unpaired electrons, then it will be paramagnetic. If it has unpaired electrons, it will be paramagnetic, and if it does not have any unpaired electrons or no unpaired electrons, it will be diamagnetic. So again, there you have it on writing electron configurations and orbital diagrams. So again, hope this was helpful, and until the next video, I'm out. Bless.